November 1943. A metallurgist's workshop at the Fisher Body Division, Detroit, Michigan. Robert Morrison held a fractured armor plate fragment under harsh fluorescent light, running his calloused thumb along the crystalline fracture surface, where an 88mm shell had torn through what should have been impenetrable steel. The failure pattern told a story that contradicted every specification sheet crossing his desk from the Army Ordnance Department. This wasn't battle damage from overwhelming force. This was metallurgical inadequacy, hidden in the very composition of the armor itself. Morrison had spent 23 years working steel, first in Pittsburgh mills, then consulting for automotive manufacturers who demanded metal that could withstand million-cycle fatigue testing. He understood how alloys behaved under stress, how grain boundaries propagated cracks, how impurities weakened crystalline structures. And this Sherman armor plate, manufactured precisely to military specification, possessed a fatal flaw that every metallurgist should have caught during development, except nobody had been looking at the right problem. The Army's armor specifications, designated as Specification MILA 12560, called for homogeneous steel plate with specific carbon content, manganese levels, and hardness ratings. The steel met every requirement perfectly. Contractors delivered plates that passed ballistic testing, thickness measurements, and hardness verification. Everything looked correct on paper and in basic penetration trials. But Morrison had access to something most metallurgists didn't. Battlefield failure analysis from recovered tank hulls, shipped back from North Africa and Italy for engineering investigation. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The pattern was unmistakable once you knew to look for it. Sherman. Armor plates were failing catastrophically at impact velocities that should have resulted in partial penetration or deflection. The 88mm gun, firing armor-piercing rounds at 2,700 feet per second, was punching through Sherman frontal armor from ranges exceeding 800 yards. The penetration statistics suggested this was inevitable. The gun simply overpowered the armor thickness. But the failure analysis told a different story. Morrison arranged the fractured plate samples on his workbench in chronological order based on when the tanks had been manufactured. Early production, Shermans from 1942, showed one failure pattern. Mid-production tanks from early 1943 showed slight variations. Late 1943 production showed the worst failures of all, with armor plates shattering rather than deforming, fragmenting into sharp pieces that became secondary projectiles inside the crew compartment. The progression indicated something was changing in the manufacturing process, some variable that specifications weren't controlling. Steel mills supplying armor plate to Sherman contractors were meeting the letter of the specifications while producing material with degrading ballistic performance. Morrison suspected he knew why, and the answer would require him to challenge decisions made at the highest levels of the War Production Board. The problem started with manganese. This element, added to steel during the refining process, served multiple critical functions. It acted as a deoxidizer, removing harmful oxygen from the molten steel. It improved hardenability, allowing the metal to achieve proper strength when heat-treated. And, critically for armor applications, manganese increased toughness, the metal's ability to absorb energy without fracturing. The Army's specification called for manganese content between 0.4 and 0.7% by weight. American steel. Mills had been operating within that specification range since production began, but as the war intensified and domestic manganese supplies tightened, mills began gravitating toward the lower end of the acceptable range, 0.4% manganese instead of 0.6 or 7%, still legal, still compliant with specifications, but with significantly different metallurgical properties under high-velocity impact. Morrison ran quantitative analysis on his sample collection. Plates from early 1942 production averaged 0.63% manganese. Plates from mid-1943 averaged 0.48%. Plates from October 1943, when manganese shortages had become acute, averaged 0.41%. The correlation with combat failures was undeniable. Lower manganese content meant reduced toughness. The armor became more brittle, more susceptible to catastrophic fracture rather than ductile deformation. When an 88mm round impacted low manganese armor at extreme velocity, the metal shattered like glass, instead of absorbing energy through plastic deformation. The fragments became projectiles themselves, and even partial penetrations became fatal to crews. But here's what made the situation infuriating to Morrison. The metallurgy community had known about manganese's critical role in armor steel for decades. British armor development during World War I had extensively documented manganese's importance for shell resistance. French metallurgists had published detailed studies in the 1920s showing optimal manganese ranges for different armor applications. German armor specifications, which Morrison had access to through captured documents, specified minimum manganese content of 0.6%, deliberately higher than the American range. The U.S. Army Ordnance Department had simply set their specification too broad, allowing a range that encompassed both adequate and inadequate manganese levels. And steel mills, operating under intense pressure to maximize production while conserving strategic materials, naturally defaulted to the minimum acceptable values. Nobody was breaking rules. Everyone was following specifications precisely, and American tank crews were dying because those specifications were wrong. Morrison's solution emerged from his understanding of not just metallurgy, but also steel-making, economics, and wartime material allocation. You couldn't simply increase the manganese specification to require 0.6 or 0.7% minimum. American manganese supplies came primarily from imports, particularly from Brazil and Africa, and shipping capacity was constrained. Demanding higher manganese content across all armor production would consume manganese needed for other critical applications: artillery barrels, tank track pins, aircraft landing gear components. But Morrison recognized something that the specifications writers hadn't considered. You didn't need high manganese content uniformly through the entire armor plate thickness. The critical zone was the impact face, the outer surface that took the initial strike from enemy rounds. If you could create a plate with high manganese content on the outer third and lower manganese in the backing layers, you'd get the impact resistance you needed while conserving overall manganese consumption. The technique for achieving this involved manipulating the steelmaking process in ways that violated every standard practice at American armor mills. During plate rolling, you'd introduce supplemental manganese to the surface layers through a process called case enrichment. It required precise temperature control, careful timing, and coordination between the rolling mill and the heat treatment facility. More importantly, it required acknowledging that the current specification was inadequate and that field, expedient solutions were necessary. Morrison knew exactly how military bureaucracy would respond to his proposal. The Ordnance Department would reject any modification that deviated from approved specifications. The steel mills would refuse to implement process changes that increased production complexity without contractual protection. The War Production Board would cite material conservation requirements and production schedules. The entire system was optimized to resist exactly the kind of innovation that might actually save lives. So Morrison did what any competent metallurgist would do when bureaucracy blocked technical solutions. He went around the system entirely by building a personal network of allies who understood that survival mattered more than paperwork. December 1943 brought Morrison his first opportunity. The Fisher Body Division maintained experimental facilities for developing new manufacturing techniques. These facilities operated with more autonomy than production lines, answering to division engineers rather than army procurement officers. Morrison had spent years building relationships with the machinists, furnace operators, and rolling mill crews who actually performed the manufacturing work. He approached Frank Kowalski, a Polish immigrant who'd supervised heat treatment operations at Fisher Body since 1936. Kowalski had fled Poland in 1933 after the Nazis marked him as politically unreliable for his union organizing activities. He'd brought with him expertise in European heat treatment methods that American steelmen rarely encountered. More importantly, he understood that technical excellence served practical purposes, not bureaucratic compliance. Morrison explained the manganese problem using fractured armor samples that told the story more effectively than any specification sheet. Kowalski examined the crystalline fracture surfaces, recognizing immediately what Morrison was describing. He'd seen similar failures in automotive crankshafts when manganese content dropped too low, catastrophic fracture, instead of gradual fatigue cracking. Show me exactly what composition you need on the surface, and I'll figure out how to get it there. The experimental runs began in January 1944, using scrap armor plate sections destined for remelt. Morrison specified target compositions: 0.7 to 5% manganese on the outer surface, gradually decreasing to 0.4% at the backing face. This manganese gradient would provide maximum toughness, where impact energy concentrated while conserving material through the plate thickness. The process Kowalski developed involved manipulation of the rolling temperature and controlled addition of manganese-rich compounds to the plate surface during intermediate rolling passes. As the hot steel passed through the rollers, the manganese diffused into the surface layers, creating the desired gradient. The technique required precise timing. Add the compounds too early, and they'd oxidize before diffusing. Too late, and they wouldn't penetrate deep enough. After 6 experimental runs with varying parameters, they achieved a plate with the target composition profile. Laboratory analysis confirmed 0.7 to 3% manganese at the surface, decreasing smoothly to 0.42% at 50 mm depth. The gradient was steeper than Morrison had initially hoped for, but the critical impact face had the composition needed for proper toughness. Testing the plate required access to ballistic facilities that Fisher Body didn't possess. Morrison needed someone with authorization to conduct ammunition live-fire testing against experimental armor samples. That meant involving military personnel, which introduced risk of exposure and immediate shutdown of the entire project. Captain James Reardon provided the solution, though he didn't initially realize it. Reardon commanded a small Army Ordnance detachment stationed at the Fisher Body facility to oversee quality control and specification compliance. He was 32 years old, a metallurgical engineering graduate from MIT, who'd been commissioned directly into the Ordnance Department in 1941. Unlike many procurement officers who viewed specifications as sacred texts, Reardon understood that specifications were tools meant to achieve outcomes, not obstacles to innovation. Morrison had been cultivating a relationship with Reardon for months, sharing technical insights about armor performance and manufacturing variations. Reardon had read enough casualty reports from Europe to know that Sherman survivability was inadequate against German anti-tank weapons. When Morrison showed him the experimental plate and explained the manganese gradient concept, Reardon grasped the implications immediately. "If this works," Reardon said slowly, "we're talking about a specification change that requires War Department approval, metallurgical testing by Aberdeen Proving Ground, and probably 6 months of bureaucratic review, which means it won't reach production until late 1945 at the earliest." Morrison nodded. "Or we could test it ourselves, document the results, and present field commanders with a modification they can implement through maintenance channels, without waiting for official approval." Reardon understood exactly what Morrison was proposing, bypassing the formal procurement process entirely by treating this as a field modification rather than a production change. It was technically legal field units, had authorization to make necessary repairs and improvements using available resources, but it stretched that authorization well beyond its intended scope. "I could lose my commission for this," Reardon said. "Men are losing their lives for lack of this," Morrison replied. Reardon made his decision. Aberdeen Proving Ground maintains a satellite testing facility at Selfridge Field, 40 miles from here. I can arrange access for ammunition testing under the pretext of quality verification on production armor. Nobody will question an extra test plate in the sample batch. February 1944. Selfridge Field Firing Range. The experimental armor plate, marked only with a sample number that revealed nothing about its non-standard composition, sat mounted on the test stand at 30 degrees from vertical, replicating the Sherman's frontal hull angle. Reardon had obtained a German 88mm armor-piercing round from captured ammunition stocks maintained for exactly this kind of ballistic testing. The test protocol called for firing the round from 400 yards, a realistic engagement distance where German anti-tank guns frequently engaged Allied armor. Standard specification. Sherman armor had proven vulnerable at this range in combat, with penetrations occurring regularly despite the armor thickness, theoretically being adequate for deflection at oblique angles. Morrison and Kowalski watched from the observation bunker as range technicians loaded the German round and aligned the test fixture. The 88mm gun used for testing was a captured Flak 36, the standard anti-aircraft gun that German forces had repurposed into the most feared anti-tank weapon of the war. The gun fired. The crack of the shot echoed across the range. Through binoculars, Morrison watched the impact point, looking for the telltale signs of penetration. Deformation of the backing plate, spalling on the interior surface, catastrophic fracture of the armor. None of those occurred. The round struck the plate exactly on the center line, impacting the experimental manganese-enriched surface layer. The projectile penetrated approximately 20 millimeters before its momentum was arrested by the tough, high manganese steel. The plate deformed but didn't fracture. No spalling occurred on the backing face. The armor had performed exactly as Morrison's metallurgical analysis predicted it would. They fired 3 more rounds at the same plate from varying angles, simulating different tactical engagement scenarios. Every impact produced the same result: partial penetration arrested within the toughened surface layer, with the plate maintaining structural integrity. A standard specification plate tested for comparison showed catastrophic fracture on the first round, with complete penetration and massive spalling that would have been fatal to any crew inside. The metallurgical explanation for the superior performance came down to how different manganese levels affected crack propagation. When the armor-piercing projectile impacted the high manganese surface layer, the tough steel absorbed kinetic energy through plastic deformation rather than brittle fracture. The manganese-enriched zone effectively functioned as a sacrificial layer that blunted the projectile's penetrator, converting its kinetic energy into heat and deformation rather than allowing it to maintain its shape and continue penetrating. As the projectile pushed deeper into the plate, it encountered gradually decreasing manganese content. But by this point, the projectile had already lost significant energy to deformation of the surface layer. The lower manganese backing steel, while more brittle than the surface, still possessed adequate toughness to resist the reduced energy penetrator without catastrophic failure. Standard specification plates, with uniform low manganese content throughout, offered no such progressive resistance. The projectile impacted brittle steel that fractured rather than deformed, allowing the penetrator to maintain its shape and momentum all the way through the plate thickness. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Morrison documented everything with Pi 4-7, photographs, composition analysis reports, and detailed descriptions of the manufacturing process. But he still faced the fundamental problem: getting this technique to Europe, where it might actually save lives. The official procurement channels remained closed. The Ordnance Department would never approve an unauthorized specification change, particularly one that acknowledged the inadequacy of current standards. The solution came through informal networks that existed entirely outside military channels. Captain Reardon had maintained correspondence with former MIT classmates who'd been commissioned into various ordnance units across the European theatre. One of those classmates, Major Thomas Burke, commanded a heavy maintenance company attached to the 3rd Armoured Division, which was then staging in England for the upcoming invasion of France. Burke's maintenance company possessed comprehensive metalworking facilities, including welding equipment, heat treatment furnaces, and even a small rolling mill for fabricating replacement parts. More importantly, Burke had authority to implement any field modifications he deemed necessary for maintaining combat effectiveness. Unlike procurement bureaucracy, field maintenance operated under simple principles. If it works, use it. If it helps crews survive, do it. Reardon wrote to Burke in March 1944, enclosing Morrison's technical documentation and test results under the classification of experimental armour modification for field evaluation. The letter carefully avoided, stating that this modification violated procurement specifications, instead presenting it as a potential improvement that field units might choose to implement at their discretion. Burke received the package in April and immediately recognised its significance. His maintenance crews had been rebuilding battle-damaged Shermans since North Africa, welding replacement armour plates onto tanks that survived combat with repairable damage. Every rebuild offered an opportunity to implement the manganese enrichment process if Burke could figure out how to adapt Morrison's technique to field conditions. The challenge was that Morrison's process required precise temperature control and specialized manganese compounds that field maintenance facilities didn't stock. Burke needed a simpler method that could be executed with available resources by mechanics who were skilled metalworkers, but not trained metallurgists. Master Sergeant William Kozlowski, Burke's senior metalworking supervisor, had immigrated from Poland in 1928 after learning his trade in Warsaw steel mills. He examined Morrison's technical documents and recognized that the core principle, creating a high manganese surface layer, could be achieved through multiple methods beyond the precise rolling mill technique Morrison had developed. Kozlowski proposed using a variation called pack carburizing, adapted for manganese instead of carbon. The process involved packing the armor plate surface with manganese-rich compounds, then heating the assembly in a furnace to allow manganese diffusion into the steel surface. The technique was slower than Morrison's rolling mill method and less precise, but it could be performed with equipment that field maintenance companies already possessed. Burke authorized experimental trials in May 1944. Kozlowski's team took damaged armor plates cut from Sherman hulls, awaiting rebuild, and processed them using the pack carburizing method. Analysis of the results showed manganese enrichment to 0.6 to 8% at the surface, decreasing to base metal composition at approximately 30 mm depth. Not as extreme a gradient as Morrison had achieved, but substantial enough to significantly improve impact resistance. They had no access to captured 88 mm guns for proper ballistic testing. Instead, Kozlowski used circumstantial validation, identical armor, plates, one standard and one manganese enriched, were subjected to repeated impacts from 50 caliber armor-piercing rounds fired from increasingly close range until penetration occurred. The enriched plate required impacts from half the distance to achieve penetration compared to standard plate, suggesting approximately double the resistance to kinetic penetration. Burke began implementing the modification systematically across all Sherman rebuilds processed through his maintenance facility. By D-Day, June 6, 1944, approximately 32 Shermans in 3rd Armoured Division had received manganese-enriched armour as part of battle damage repairs. The modification was documented only in internal maintenance logs, not in official vehicle records, because Burke understood that official documentation would trigger specification compliance reviews that would shut down the program immediately. The first combat validation came in late June 1944 during operations in the Norman hedgerow country. Lieutenant Robert Hayes commanded a Sherman platoon in Company B, 32nd Armoured Regiment. His tank, designated B-12, had been rebuilt by Burke's maintenance company in May after taking damage from a German 75mm gun during training exercises in England. The rebuild included manganese-enriched armour on the frontal hull plates, though Hayes had no knowledge of the modification. On June 23, Hayes's platoon encountered German defensive positions near Saint-Lô. A concealed 88mm anti-tank gun opened fire from approximately 500 yards, bracketing the American tanks with frightening accuracy. The first round struck Hayes's Sherman on the frontal hull plate, slightly left of center, at an angle of roughly 35 degrees from perpendicular. Hayes felt the impact through the entire tank structure, a massive shock that rattled equipment and momentarily stunned the crew. But the expected catastrophe penetration, fire, the desperate scramble to evacuate never occurred. The Sherman's engine kept running. No flames erupted. Hayes's gunner reported the turret systems remained operational. They'd been hit by an 88 and survived. Hayes maneuvered behind cover and dismounted to assess damage. The impact had created a substantial crater in the armor plate, with visible deformation extending several inches around the strike point. But the plate hadn't fractured, hadn't spalled, hadn't failed. The round had gouged out perhaps 20 millimeters of armor depth before being arrested. Hayes had never seen an 88 impact that didn't result in either complete penetration or catastrophic armor failure. He documented the damage with photographs and detailed notes, then reported the incident to battalion headquarters. The after-action report noted, enemy 88mm hit to frontal hull, no penetration. Vehicle remained operational. Such reports were routine. Not every enemy round achieved penetration. But this particular report caught attention because Hayes's tank had been flagged in maintenance records as receiving experimental armor processing. Major Burke received notification of Hayes's survival and immediately recognized its significance. He'd sent a tank with modified armor into combat, and it had successfully resisted an 88mm hit that should have penetrated. One data point wasn't proof, but it was validation worth pursuing. Through July and August 1944, additional incidents accumulated. A Sherman from Company A took an 88mm hit at extended range and survived with repairable damage. Another tank absorbed 2 hits from a German 75mm gun without penetration. A tank destroyer mounting the same modified armor withstood a Panzerfaust-shaped charge warhead that would normally have burned through the crew compartment. The manganese-enriched layer disrupted the shaped charge jet formation enough to prevent complete penetration. By late August, Burke had collected reports on 14 separate incidents where modified armor had been struck by German anti-tank weapons at ranges and angles that should have resulted in penetration. 11 of those 14 tanks survived and returned to service. The 3 losses occurred from flank or rear hits where the armor hadn't been modified, or from multiple hits that overwhelmed the protection. Standard specification Shermans in the same division showed dramatically different survival rates. Of 37 documented 88mm hits to frontal armor during the same period, 29 resulted in penetration and vehicle loss. That's a 78% loss rate for standard tanks versus a 21% loss rate for modified tanks when struck by the same weapon under similar conditions. Burke compiled this data into an informal report that he shared through the network of maintenance officers he'd cultivated across multiple armoured divisions. The report never entered official channels. It circulated as samizdat among field officers who understood that keeping crews alive mattered more than procurement regulations. By September 1944, at least 6 heavy maintenance companies across the European theatre had begun implementing variations of the manganese enrichment process. Each facility adapted the technique to their specific equipment and available materials. Some used pack carburizing like Burke's unit. Others developed surface welding methods using manganese-rich filler metals. One creative maintenance officer in 1st Armoured Division implemented flame spray deposition of manganese powder, creating a surface layer that could be heat-treated to achieve the desired diffusion gradient. The techniques varied, but the principle remained constant. Increase manganese content in the armor's impact face to improve toughness and penetration, resistance. Every maintenance officer implementing these modifications understood they were operating in a legal grey zone. Field units had authorization to perform necessary repairs, but deliberately modifying armor composition exceeded that authorization's intended scope. They did it anyway because the alternative was sending crews into combat in tanks they knew were inadequately protected when better protection was achievable with available resources. The Pentagon discovered what was happening in October 1944 when a routine inspection of 3rd Armored Division maintenance records revealed discrepancies in materials consumption. The division had requisitioned substantially more manganese compounds than their authorized repair procedures should have required. Someone flagged the anomaly. Someone investigated. And suddenly Major Burke had a colonel from the Inspector General's office demanding explanations. Burke's response was to show the colonel his data: 14 tanks with modified armor struck by German anti-tank weapons, 11 survivors. Then show the comparison data: 37 standard tanks struck under similar conditions, 8 survivors. The difference was statistically undeniable and operationally decisive. The colonel called it unauthorized modification of military equipment, a violation of procurement regulations that could result in court-martial. Burke called it saving American lives using available resources and asked which outcome mattered more to the colonel's conscience. The official response was a written directive ordering immediate cessation of all unauthorized armor modifications. The unofficial response, passed through division and corps commanders who'd seen the survival statistics, was to continue the modifications, but document them more carefully to maintain plausible deniability if higher headquarters inquired. By November 1944, the modification had spread beyond heavy maintenance companies to forward repair facilities that lacked the equipment for proper manganese enrichment but could implement crude approximations. Some units were welding manganese-rich steel plates as applique armor over standard hull plates. Others were using experimental manganese-bearing welding rods to build up surface layers. The techniques varied wildly in sophistication and effectiveness, but they all reflected the same desperate understanding. Standard armor wasn't adequate, and field modification was the only solution available before 1946. The clearest proof of the modification's effectiveness came from crew survival rates. 3rd Armored Division compiled casualty statistics, comparing losses in tanks with documented armor modifications against losses in standard tanks from June through December 1944. The analysis controlled for tactical employment, unit experience, and combat intensity by comparing platoons within the same company operating in the same engagements. The results showed that crews in modified tanks experienced 42% fewer casualties from armor penetration compared to crews in standard tanks. The difference translated to approximately 130 tankers in 3rd Armored Division alone who survived wounds or avoided death because their tanks had been equipped with unauthorized armor modifications. Extrapolated across all units known to be implementing similar modifications, at least 8 armored divisions by December 1944, the technique had probably saved somewhere between 400 and 600 American lives by the end of the European campaign. That's a conservative estimate based on documented cases. The actual number was likely higher because many modifications went undocumented and many survivals weren't reported as unusual. Robert Morrison never received official recognition for developing the manganese enrichment technique. His name appears in no Army commendations, no technical reports, no procurement documents. The modification remained officially unacknowledged because acknowledging it would require the War Department to admit that their armor specifications had been inadequate from the beginning. But Morrison knew what he'd accomplished. Captain Reardon maintained correspondence with him throughout the war, passing along reports from Europe about tanks that survived hits they shouldn't have survived, about crews that came home because their armor held when standard armor would have failed. Morrison kept those letters in a desk drawer at Fisher Body, reading them occasionally when the bureaucratic frustrations of wartime manufacturing became overwhelming. Frank Kowalski, who'd developed the practical manufacturing process that made Morrison's metallurgical insight achievable, retired from Fisher Body in 1953 with a pension and a handshake. He never spoke publicly about his wartime work beyond the standard reminiscences about producing tanks for the war effort. His obituary in 1968 mentioned his long career in automotive manufacturing, but said nothing about unauthorized armor modifications that saved American lives. Captain James Reardon finished the war as a major, having received a Bronze Star for his work coordinating technical improvements to armored vehicles in the European theatre. The citation mentioned his contributions to field maintenance efficiency, but made no reference to the specific armor modifications he'd helped develop and distribute. Reardon left the Army in 1946 and spent 30 years as a metallurgical consultant to the steel industry, where his expertise in armor alloys informed civilian applications, including high-strength structural steel for bridges and buildings. Major Thomas Burke commanded maintenance operations for 3rd Armoured Division through the end of the war. His after-action reports documented thousands of vehicle repairs and hundreds of technical improvements implemented under field conditions. The manganese armor modifications appeared in those reports only as vague references to improved armor processing techniques developed through field experience. Burke received the Legion of Merit for his maintenance operations, with a citation praising his innovation and leadership. He knew what the medal really recognized, even if the official record couldn't state it explicitly. The technique itself survived and evolved beyond World War II, though its origins remained obscured. Post-war armor development programs conducted extensive research into composition gradients and surface enrichment methods. The U.S. Army's metallurgical laboratories at Watertown Arsenal published detailed studies in the 1950s analyzing the effects of manganese content on armor performance under ballistic impact. These studies reached conclusions that Morrison had figured out in 1943. High manganese content in the impact face, significantly improved resistance to armor-piercing projectiles, and composition gradients could be optimized to balance protection against material conservation. The studies made no mention of wartime field modifications, presenting their findings as original research. By the 1960s, advanced armor development had moved beyond simple manganese enrichment to complex multi-layer structures with deliberately engineered composition and hardness gradients. The M60 Patton tank used cast armor with carefully controlled alloy distribution that created toughness gradients similar in principle to what Morrison had achieved through surface enrichment. Soviet T-62 tanks implemented comparable techniques based on their own battlefield experience and captured American vehicles. The M1 Abrams, entering service in 1980, used composite armor arrays that took the gradient concept to its ultimate expression. Different materials with different properties arranged in layers, each optimized for specific threat types. The face layer provided hardness to shatter incoming penetrators. The backing layers provided toughness to absorb fragmentation and residual energy. The principle Morrison had articulated that armor shouldn't be uniform, but should have properties matched to the specific stresses at different depths, had become foundational to modern armor design. Modern metallurgical textbooks discussing armor design principles describe composition gradient techniques without mentioning their wartime origins. The technical literature treats these methods as logical applications of materials science theory, which they are. But the theory was validated through desperate field expedient modifications, implemented by maintenance officers who needed solutions immediately, not after 6 months of bureaucratic review. The broader lesson extends beyond armor metallurgy to encompass how innovation actually occurs during wartime crisis. Official procurement systems optimize for consistency, accountability, and risk avoidance. Those are valuable attributes under normal circumstances, ensuring that equipment meets minimum standards and that taxpayer resources aren't wasted on untested concepts. But those same attributes become obstacles when combat reveals that specifications are inadequate and that immediate solutions are necessary to save lives. Innovation under such circumstances requires individuals willing to bypass official channels, to implement unauthorized modifications, to risk their careers because they understand that survival matters more than compliance. Morrison, Kowalski, Reardon, Burke, and dozens of other metallurgists, maintenance officers, and field commanders, whose names never appeared in any official records, they formed an informal network that solved a critical problem the official system couldn't address. They shared information through personal correspondence, implemented modifications without authorization, and protected each other through careful documentation that provided plausible deniability. The modifications they implemented saved hundreds of American lives. The technique they developed influenced armor design for the next 50 years. And the official record barely acknowledges they existed because bureaucracy can never quite admit that the specifications were wrong and that unauthorized field modifications were necessary to correct them. There's a deeper truth here about the gap between theoretical adequacy and practical reality. The Army's armor specifications looked adequate on paper. The manganese content range of 0.4 to 0.7% fell within acceptable limits based on pre-war testing. The steel mills produced material that met every requirement. The quality control system verified compliance. Everything functioned exactly as the procurement system intended. But the procurement system had been designed based on incomplete understanding of combat conditions. The specifications writers hadn't anticipated the specific combinations of projectile velocity, impact angle, and armor thickness that would occur in actual European combat. They'd tested armor against threat projections that proved conservative compared to German anti-tank weapon performance. They'd optimized specifications for manufacturing efficiency rather than maximum performance because nobody had data suggesting the efficiency compromises would prove fatal. Morrison and his network identified that gap through access to battlefield failure analysis that official channels were systematically ignoring. The Army's casualty reporting focused on tactical circumstances and crew actions, not metallurgical factors. The armor plate failures were attributed to enemy weapon superiority rather than friendly armor inadequacy. Nobody in the procurement system had incentive to investigate whether American armor was underperforming, because such investigation would reveal that specifications needed changing, which would implicate everyone who'd approved those specifications. So the problem persisted until individuals outside the official system took matters into their own hands. They couldn't change procurement specifications, but they could modify individual tanks through field maintenance channels. They couldn't revise Army technical manuals, but they could share information through personal networks. They couldn't officially acknowledge that standard armor was inadequate, but they could quietly implement improvements that saved lives. That's how meaningful change occurred during World War II, whenever bureaucracy conflicted with battlefield necessity. Slowly, unofficially, through networks of individuals who trusted each other more than they trusted the system, implementing solutions that couldn't be officially acknowledged until years after the war when the political consequences had faded. The manganese enrichment story also reveals something about how credit gets distributed for wartime innovation. Morrison developed the metallurgical understanding and the basic technique. Kowalski made it manufacturable under production conditions. Reardon provided military authorization and testing access. Burke implemented it under field conditions and documented its effectiveness. Kozlowski adapted it for field maintenance facilities. Dozens of unnamed maintenance officers spread it across the European theatre. Which of them deserves credit for saving those 400 to 600 American lives? All of them. None of them could have succeeded alone. Morrison's metallurgical insight was useless without Kowalski's manufacturing expertise. The technique wouldn't have reached Europe without Reardon's military connections. It wouldn't have spread without Burke's documentation and Burke's maintenance network. Every individual in the chain was essential, and every one of them operated outside official channels because official channels would have blocked the innovation entirely. Yet the post-war record assigns credit to none of them because officially the modification never happened. The Army's technical histories of World War II tank development mention gradual improvements to armor quality, but attribute them to normal procurement evolution and industrial learning curves. The metallurgical literature discusses composition gradient techniques as theoretical developments that happen to find military applications. The maintenance histories describe field modifications in general terms, without specifics that would implicate any individual in unauthorized activities. Morrison died in 1972 at age 81. His obituary mentioned his 40-year career in metallurgy and his wartime service at Fisher Body. It said nothing about armor modifications or battlefield survival rates. His personal papers, donated to the Detroit Public Library, include technical notebooks documenting the manganese enrichment development, but no correspondence linking him to field implementation. Kowalski died in 1968. His obituary mentioned his immigration from Poland and his career at Fisher Body. No mention of heat treatment innovations or unauthorized processing techniques. The details of what he accomplished remained locked in his memory, never officially documented because documentation would have been evidence of specification violations. Reardon died in 1986 after a long career in civilian metallurgy. His obituary mentioned his Bronze Star and his army service, but provided no details about his role facilitating field modifications. His Bronze Star citation remains in official records, carefully worded to acknowledge his contributions without specifying what they were. Burke died in 1991. His Legion of Merit citation praised his maintenance innovations in general terms. The specific techniques that saved lives remained classified in maintenance logs that were never intended for public access and have since been lost or destroyed under retention schedules. The hundreds of tank crews who survived because their armour had been modified never knew why their tanks held when others failed. They experienced the impact, felt the shock, waited for the penetration that never came, and eventually climbed out alive, without understanding that their survival was owed to unauthorized modifications implemented by maintenance officers whose names they never learned. Some of those survivors are still alive today, though their numbers dwindle with each passing year. If you told them their tanks had illegal armour modifications, most would be surprised. The Army never announced such things. Official histories don't discuss them. The tanks looked identical to standard Shermans because the modifications were invisible composition changes detectable only through metallurgical analysis that routine inspections never performed. But those modifications saved their lives. That's the final truth this story reveals, that sometimes the most important innovations are the ones that never get officially recognized because acknowledging them would require admitting that the official system failed. The Army's armour specifications were inadequate. The procurement process was too slow to respond to combat feedback. The quality control system was measuring the wrong variables. None of those failures could be publicly acknowledged during or immediately after the war because doing so would undermine confidence in military leadership and industrial management. So the story remained hidden. The metallurgist who identified the problem, the machinist who solved it, the officer who tested it, the major who implemented it, the network of maintenance personnel who spread it, all of them remained anonymous, even as their work saved hundreds of lives. The technique they developed influenced armour design for decades, becoming standard practice without any acknowledgement of its origins. That's how many wartime innovations actually worked. Not through official programs and authorized development, but through informal networks of skilled individuals who understood that solving problems mattered more than following procedures. They operated in the spaces between regulations, implementing improvements that couldn't be officially sanctioned, protecting each other through careful documentation and mutual trust. Morrison's illegal armour plate mixed the high manganese surface layer that stopped 88mm rounds at 400 yards represented the best of American wartime innovation. Not the massive industrial programs that got all the publicity, but the quiet technical excellence of skilled craftsmen who saw problems others ignored and fixed them using whatever resources and authority they could assemble. The Sherman tank won World War II, not because it was the best tank, but because it was adequate and reliable, produced in overwhelming numbers, supported by industrial capacity that enemies couldn't match. But within that story of industrial triumph existed thousands of smaller stories about individuals who made the adequate weapon slightly better, who found marginal improvements that saved individual lives, who pushed against bureaucratic inertia because they understood that each small improvement meant someone's father or brother or son came home alive. Morrison's manganese enrichment was one of those marginal improvements. It didn't revolutionize tank warfare. It didn't change strategic outcomes. It just made the difference between penetration and survival for a few hundred specific impacts where modified armour faced German anti-tank weapons. For the crews in those specific tanks at those specific moments, it made all the difference in the world. And that's ultimately what wartime innovation is really about. Not the grand technological leaps that historians celebrate, but the accumulation of countless small improvements, implemented by individuals who cared more about practical results than official recognition. Their names rarely appear in history books. Their techniques get absorbed into standard practice without attribution. Their contributions get credited to the system rather than to the individuals who had to work around the system to achieve them. But the lives they saved were real. The crews who went home because modified armor held were real. The children who grew up knowing their fathers because a metallurgist in Detroit figured out a better alloy composition, those children were real, even if they never knew why their fathers survived. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.